Okay, so welcome back again for this last talk, I think, this session. So given by Elena Celledoni from Norway, so about deep learning as optimal control problem.
Thank you very much. Thank you for coming to the talk. It's the last talk of this sampling on manifolds week of activities, and I'm going to talk about this project that we did together with Martin Benning, Matthias, Ehrhardt, Brynjulf, and Carola. And in the second part of the talk, I will talk about descent methods that can be applied to problems of deep learning. So the talk is divided in two parts. So the background or the theme of the talk is somehow geometric numerical integration and structure preserving algorithms and how they come into deep learning problems. I need to use this. Okay. All right. So the first part is about this deep learning as optimal control. This is work inspired by some earlier work by Haber and Rutotto and by the group of Weinani, but also work that was appeared much earlier by LeCun in the 1980s, late 1980s. So what is this interesting for? The interest is the fact that you would like to use this interpretation in order to design new algorithms, new good algorithms, to have more efficient training of deep neural networks, and to have algorithms that generalize well. And we have already discussed this earlier with Ben and with our informal discussions yesterday, especially. So, but I will recall what I mean by that. Okay, so crash course artificial neural networks very quickly, how I think about it. So a network, artificial neural network can be depicted by a picture like the one you see on the board now. And on the left-hand side, let's see, I can use the pointer. On this side, you have the input, and the input is the data that you are inputting to your network, and it's mapped through the network until you reach an output. So you can think of this picture as a composition of maps where you have an input, which is the input data, and an output, which is given by applying successively all these maps. Each of the maps here, there is an index here. L is the number of layers, so these columns are the layers. The index typically doesn't necessarily mean that you have a completely different map from one layer to the other, but you have different parameters. So the map depends not only on the input at layer L, but also on the parameters UL. And these are parameters that typically you want to find, you want to determine. So in order to have, so this is the artificial neural network, but if you want to do learning with artificial neural networks, what you need is a cost function. To establish somehow a cost function over that depends on the output of the neural network, and it's a sum over all possible inputs. So your data is the input, and is given in a space of where the data lives, and you run the data through the network, get the output, and then you are able to compute the cost function. Oops. Oh, yeah. Green. All right. So you have an optimization problem at this point when you have this cost function that you want to minimize. You minimize the cost function and you determine your parameters, your unknown parameters. The larger is the number of columns here, the larger is the number of maps you're composing, the larger is the number of parameters that you have to determine. So in order to solve these optimization problems, the usual strategy is to use stochastic gradient descent. Deep learning means that you have a large number of columns in your network. And it is said in the literature that it's important to consider deep learning for certain learning tasks, like for example for visual recognition, but also perhaps for activity recognition, which is a similar kind of task. And that type of task would require that your data, perhaps not require, but it would be natural to require that your data is living on a manifold or is manifold valued. Problem with this is that deep neural networks are typically more difficult to train. So, in other words, they lead to optimization problems which are more difficult to solve. And here is the proof or the background about this paper, for example, from 2016, where I took this picture from. And you can see that for a plain feed-forward neural network, we have this effect on the gradient descent iterations, that the 34-layer network gives you a worse error than the 18-layer network. And similarly, on the other hand, if you use the right architecture, so not a simple neural network, but a special one, which is called ResNet, then you are able to improve your error in the gradient descent by augmenting the number of layers. Okay? But in general, so this tells you it's not so trivial to add layers and to get a better, more predictive type of neural network. And this fact here that you have this step type of behavior means that you have vanishing or exploding gradients. And clearly, this network works better than this other one. So let's. This
is showing the error on verification data. Or
there are two. One is training. The thick line is training, and the other one is test. But I don't want to stress too much this thing. Okay, so let's have a look closer to ResNet, how it looks. So in particular, we're going to look how a typical map for ResNet will look like. And the format is as follows. You take the layer L, the output at layer L, and you add some correction. And so your map has a special format, very simple. The F is called residual, and the UL, so the parameters that you're going to learn, are a matrix which has the same size of the data, and a vector which has the same number of components of the data. So what I'm going to do as a first step, I'm going to modify the ResNet by introducing an extra scalar parameter here, HL, which will give me back the same thing if I put all HLs equal to 1. Okay, so it's a trivial modification. And I do this for reasons that will become clearer later. So just to add some more detail on how a typical ResNet would be, the F, the residual function F here, has this format here. So it's a linear or it's an affine transformation of the data with this matrix of parameters and the bias vector, to which I, in the end, apply a nonlinearity, which is, for example, one of these two functions. So either a hyperbolic tangent, the sigmoid, or the ReLU that also Ben had in his talk.
Is this component-wise, or how do you apply?
Component-wise. Component-wise, very special type of nonlinearity. And the cost function is also something important. It's a sum of contributions on all the data one by one. This is also something that is important because it's the basis of the stochastic gradient descent in some sense, that you can compute gradients of each of the parts here. And we'll have this format typically, where here C is the label which is representing the truth of the datum in input. So you know something, if you have a supervised learning type of problem, so you know something about your training data, you know that, for example, there is a cat or a dog in your image, and you will put this into this vector. And here, in the end, once you have sent through the data through the network, what you're doing here is you sort of transform it into a way that can be compared to the truth. Okay?
So C is part of Y in.
C
is a part of Y in. It's a C in.
C, it goes together with Y. It's the label, so your data comes together with the label. Okay, let's summarize. So here I put everything that I told you so far. And in this box, I want to just state the deep learning problem for the ResNet architecture. So we are going to minimize over the parameters that go from over all layers the cost function. Now I use this notation for the cost function for the whole sum, okay? Subject to this relationship here. So these maps that map from layer to layer. And the initial value is the input data, and once I have gone through all the layers, I will have my output data. Okay, this is quite similar to an Euler step for integrating this ODE. And this is the key to see this as an optimal control problem. And this is what I'm going to show you in the next slide. So this is what was realized by these people in their papers. So you can, in the limit, as the number of layers go to infinity, you could think that your problem looks like this. So, and you will have a continuum of parameters that you're going to look for. Okay, so this point of view says this is useful. Okay, why is this useful? Well, it states the optimal control problem in deep learning problem in 2 lines. It's a very simple formulation. It is a way to create new architectures. Now we're discretizing this, and we can create a new way of a new neural network. And then it's a good point of departure for analyzing the problems, because experience shows that continuous models are useful to analyze things. Okay, so this is my point. Moreover, it has attracted quite a lot of attention in the last few years, and this is just a sample of the references of people who have been working on this point of view of optimal control. Okay, what did we do? What did we contribute? Well, so we were intrigued as well by this point of view, and first of all, we wanted to look at the numerical analysis of it. We wanted to see what is the obvious way of discretizing such an optimal control problem, and so you want to derive first order optimality conditions for the problem, and then this leads to a Hamiltonian boundary value problem. Then we wanted to see what is the effect of applying different Runge-Kutta discretisation to the problem. And this led to find out that the right way to do it is symplectic partition Runge-Kutta methods, and that this way you get explicit formulae for the gradient. So this gives you explicit formulas for the gradient. So we have implemented this, and I'm going to show you a number of experiments that we have done with this. And one thing that is also quite intriguing is that we have included learning the step size of the algorithms, which is a little bit related to what Ben was talking about before, this, I don't remember, scaling symmetry, as you called it, something like that. Okay, so first point, the first order optimality conditions of the optimal control problem can be stated like this. They are a Hamiltonian boundary value problem. So here, the Hamiltonian function is a simple one. It's given like this. Okay? And it is a differential algebraic equation. You have a constraint down here, and it has index 1. No, where is my, okay. So you see, or I want to argue that symplectic partition Runge-Kutta methods are the right way of discretizing this. It's quite well known, in fact, in the literature for optimal control problem. And the reason is that they respect the variational nature of the problem, also under discretisation. And let me say this schematically, what it means. If I have my optimal control problem, and I discretize, so I choose a Runge-Kutta method for this problem, for example, and then I get a discrete problem down here, and I optimize with respect to the discrete parameters. Here I have parameters which I didn't emphasize, but a u that is continuous, and here down here I will have a discrete number of parameters. Okay. Now I optimize with respect to these parameters, I get something. And what is that? It's the same as if I first optimize, I obtain my boundary value problem, and then I use the same Runge-Kutta method phi here to solve the first equation, and the matching Runge-Kutta methods to solve the second equation. So in such a way that the two together give me a partition symplectic Runge-Kutta method. And if I do so, what I obtain is the first order optimality conditions for this problem here. Okay? So optimize, discretize, optimize commutes with optimize, discretize in this setting. Okay?
Just a small question. So here, when you say discretize, is nothing to do with because you started with something that was discrete to get to continuous, but that was discrete in the number of layers. But continuous.
No, it's the same. It's the same. But you can say that you can say, good point. You can say that you start from the discrete,
yeah,
and you have the continuous. You could go like this in the diagonal, right?
Yeah.
And this will give you, what I'm going here now. This will give you, through this problem, another way of discretizing or creating new problems. Okay. So one thing that you should not know, if you want to approach this problem directly, is to use the same Runge-Kutta method for solving this and this, because that would not correspond to optimizing a discrete problem, and that typically leads to inconveniences, to order reductions in Runge-Kutta methods. Okay, so this is the same thing, but for the couple of forward Euler, backward Euler symplectic pair. Okay, so it's the same idea that I explained before. So out of this little theorem, what you can get is in fact explicit formulas for the gradients of the cost function with respect to the parameters. And these are given in terms of the quantities which are arise naturally in the Runge-Kutta method. Okay? So if you apply your partition Runge-Kutta method, then you get some building blocks that you could put together, and those and with the correct formulas you get the gradients out. Okay, classical literature on this type of problems is due to Hegel, and there is a recent review of Sanserma on this topic, on optimal control problems. Okay, here is the algorithm, the way we implemented it. So we have to integrate forward in time this equation. We go through all the layers. We obtain the last value. We use that in order to compute the boundary value for the variable p, which is at the end of the time interval. And then we integrate this equation backwards in time. And once we are at the first step, we are able, or underway, we are able to compute the gradients with respect to the corresponding parameters. Once we have updated all the gradients, we can do a step of gradient descent in order to determine the parameters. Okay? So this is the way we are solving it. Instead of solving all the equations at once, we do this iteratively. So we do first this part, then this part, and then update the gradients and make a step of gradient descent.
So just to be sure, so here there is an initial condition in y on a final in p.
Yeah, so you have to generate, you have an initial condition, yes, that's right.
There is a y0 on a p n.
Y0 is the data.
Y0 is the data, and yeah. So the Hamilton-Pontriaghi in principle gives you that. Okay, let's have a look at some of the experiments. And these are similar experiments to what Ben was describing before. So here is what I'm showing is 4 different Runge-Kutta methods with different orders. This is the ResNet, or Euler method. This is order 1, order 2, and order 4. And what you see on the top line is the prediction. So the light dots are the data, and the dark red and dark blue are the prediction. So we have blue dots and red dots. We want to see which area of the plane is going to be predicted to be red and which area of the plane is going to be predicted to be blue. Okay, and this is what you see up here. Down instead, what you see is how the dots have been moved through the network. So the ODE is, you can think that the ODE is taking your input data and flowing it to some other position. And the final position is such that all the blue dots are on one side, all the red dots are on the other side, if you are successful with your classification. And you can divide them with a line.
That only makes sense because you have 2 nodes at each layer. Is that right? Yes. So you can keep thinking of it as a planar map.
Yeah, yeah, right. Otherwise, it would be more difficult to visualize everything, right? So, yeah. Okay. So there is not much difference in between the various methods, you can say. So one of the conclusions of the paper is that using different Runge-Kutta methods doesn't really give you such a big difference. Perhaps there is a little bit of a difference in between order 1 and order 2, but not much otherwise. So this can say that perhaps the ODE is the thing that matters rather than the numerical methods that you're using. And here is again the same 4 methods, and you see now how the points move throughout the layers, okay? Throughout the time, the integration time. So how from the initial configuration, they are mapped to the final configurations. And this is, again, you cannot see really big differences in between the different methods. This is something that we have done by optimizing the step size. Again, we have different methods in the different columns. The first method is a simple feed-forward neural network, and that is not very successful in this classification problem. The second one is the ResNet, so it's the Euler method, you can say. The third one is the ResNet, but with variable step size, where the step size has been learned. So it's a parameter that has been optimized for. And the last one is, again, something like that, but we have in addition a constraint, a simplex constraint on the step size. So while these two are quite similar, in this case, I don't see these very strange interfaces that you had in your problems. They are quite smooth, my interfaces, even if they are sharp.
I should have mentioned that's likely an artifact of the initialization that we use, because we use basically null initialization in those ones that gave the very jagged classifiers. You probably used normal random variables for your initializations.
I don't remember that.
Common.
And but there is quite a big difference in this last one, which has been done with a simplex constraint. So here, in fact, there is quite a difference. Okay, this has been. These are the same methods applied to the MNIST database, and we have made it into a binary classification problems, because our paper was just about binary classification, so we didn't want to add complexity to things. But what you see is how the methods perform, so the accuracy of the methods throughout the gradient descent iterations. And also what you see is how the step size is selected by the optimization. So one method, the ResNet with orange here, is constant step size, while the other two have learned step sizes. So the step size is varying, and what is very strange is that the ODNet with simplex is in fact having 0 step size in most steps, except 2 or 3. So the behavior is, if you look at how the points are moving, you see that is quite erratic and quite discontinuous. So they are separated by 2 or 3 strange moves.
How does it work if you replace gradient descent by atom, for example, or RMS prop?
That I have not tried.
And the yellow was a negative step size?
Negative step size.
What does it mean? It's
Yeah, also the referee asked that. But then the answer is okay, but I mean, we do this all the time in splitting methods.
Maybe if this
High
is
order
called,
splitting methods, not first or second order. Huh?
maybe if this is called learning, then pushing it back to another layer is called thinking.
Yeah, very good, very good. Thinking and learning algorithms.
You have the answer to the referee.
Sorry? You
This
should.
is the answer to the referee.
maybe it was.
Okay. So here is a bit of a summary, because I want to change subject in the next 10 minutes. I think I've already said a little bit of what is written here, so I don't go through this. So what I want to discuss now is go into the detail of many of descent algorithms or ways of accelerating the gradient descent, which are very popular and very well known in the optimization literature, and look at them from the point of view of ODEs. Okay? So there are a number of ways of accelerating gradient descent by looking at Hamiltonian systems. So this is something that we are familiar with from molecular dynamics. We have been looking at things like that almost for 2 days now. So what you do is you put up an Hamiltonian system that has this Hamiltonian function here, and you add some linear dissipation. Okay? So gamma is positive, and turns out that the energy here is dissipated, is diminishing, and if U star B star is an equilibrium point, so if the gradient is 0, then also it's the gradient of J, which is the one, it's the function that you want to minimize, is going to be 0 as a consequence. Okay? Okay, so what you want to do with this equation is to integrate it with a simple integration, which is dissipating the energy. Such, if the dissipation is linear, this is called conformal Hamiltonian system. And then there is a way of understanding, the way of defining conformal symplectic methods as well. Okay, so back to this system, a very popular method for optimization is this Polyak heavy ball method, which is a simple integration with forward Euler for the first equation and backward Euler for the second equation. It's a partition Runge-Kutta method for this, and it's you can prove that it's conformal symplectic. Another very popular method is the Nesterov accelerated method, and that is something like Sturmer-Vallée integration of the same system. Okay? But not immediately, not directly on the system. What you need to do first is to change the variables by pre-multiplying the p by this exponential. Okay? So first change variables in your system, get a new system with p tilde as a variable and u, because you don't do anything to u, and then you apply a Sturmer-Vallée on the obtained system, and out comes this Nesterov accelerated gradient method. So this one is conformal symplectic, this one is not conformal symplectic. Turns out that another method is this relativistic optimization type method, where you replace the kinetic energy with, which was before just P transpose P divided by 2, by something like this. This is the bounded kinetic energy. So based on this kinetic energy, you can show that the very popular Adam method is just this integrator for the new system. And this is very, very popular and works very well. Of course, what is crucial in all these methods is how you choose the step size, how you choose the dissipation parameter gamma, how you choose these other parameters.
But Adam uses this history, and it uses an individual one, like for each component too, right? It uses a different time step essentially in each component, and a history.
I don't know, there are various variants of the same method. So
Okay. Adam-like.
I think, okay, Adam-like. One thing that is kind of a nice observation is that these systems here, they can be cast into the framework of Port-Hamiltonian systems. So Port-Hamiltonian systems, they have this format here. So now I put P and U into a variable X, I put them together. X is the state. Now this part here corresponds to this part. So it's the gamma p part. And y is the output. It's defined, typically it's defined like this for this type of problems. So it's a modification of Hamiltonian systems. Omega could depend on x in the general setting. And this part is a control type of part, okay?
Elena, what do you require of the G?
What do you require of the G? You don't require very much. I don't. Perhaps I have a good answer somewhere in my head, but I don't. Okay. So why are these systems interesting? Because again, they can be easily, systems like that are energy preserving when you cancel this part, when gamma is equal to 0. And energy dissipative can be made energy dissipative with the wise choice of the input of the gamma part. Okay? And in the previous situation, we had the gamma was multiplying minus p, but in general, you could have a g which is more complicated. For example, it could depend both on p and u, and also on the integral of u. That is the situation of PID controls. However, in the case where you can write this part, another interesting thing about these systems is that they are stable under interconnection. So you could have two of these with different variables, and you could use the input of the output of one of them to be the input of the other, okay? And still maintain the same structure. Okay? If you do this interconnection of the two systems in a good way, in a proper way, then you still have something that has the same structure. So an Hamiltonian function of a similar type. I mean, it's the sum of the two Hamiltonian functions. Okay, however, in the case that we've seen so far, where this part was just depending on p, then in fact what you have is that you can write your whole this term as a matrix A times the state variable x. And in that case, what you can do is to make a change of variables like Nesterov did in his method, and or perhaps he didn't do it, but did it anyway. And then you can, by this change of variable, rewrite your system in this form, where now omega has this format, and the energy is changed to be like this. And then you can, for example, play around, if you like, and I did this for this talk, and create integrators for this new problem, for example, or exploit the PID formulation. Okay, here is a comparison of all the methods for a typical optimization, simple optimization problem, simple but difficult. So it's a 2D problem, but it's a typical text problem. And here you can see the gradient descent with backtracking is not performing very well. This is the heavy ball problem, heavy ball method, and these are the other three, so they are comparable. This is very much depending on the initialization, on the choice of parameters, and so on and so forth. So it's not extremely representative, but it's true that you can accelerate the gradient descent with this method. I thought this sort of thing is quite interesting because it puts these methods into the perspective of what we know and what we love from for example, molecular dynamics, but also from mechanical systems. Okay, here is a number of references. We have done some work in energy preserving and passivity preserving methods for port Hamiltonian systems, so methods that dissipate the energy. But of course, there is work done already in 2000 about conformal simple Hamiltonian systems, and here it's literature from DeepMind, people from DeepMind, and so on. Okay, now I'm going to conclude soon, and this is related to what we started discussing during this week. And so what do you do with machine learning algorithms? In reality, is estimating probability distribution, which are parameterized with respect using the parameters of the neural networks that you're learning in your neural network. Those probability distributions belong to a finite dimensional manifold, which is parameterized with those parameters. And gradient descent or Hamiltonian descent on this manifold would work better than ordinary gradient descent or Hamiltonian descent if we knew what kind of metric to use and what kind of manifold we are on. Okay? So this is a bit similar to what Ben was saying. So problem is how to describe this manifold and what are adequate constraints for theta and what are the adequate metrics. If we had that, then we could use gradient descent on this Riemannian manifold. So if we know how to parameterize the manifold or how to make constraints appropriately, then we could use gradient descent, Riemannian gradient descent on those manifolds. So we have done recently some work on gradient descent and discrete gradients on Riemannian manifolds, and in particular for gradient flows we have been considering Ito-Abe methods. This is a sort of coordinate gradient descent. It's very simple. It doesn't require to compute derivatives, and it can be randomized. And that is very important in non-convex optimization. And here is some references, and what would like to point out this interesting and very good thesis by Erlen on discrete gradients and randomized Ito-Abe methods for optimization in all sorts of situations. And a very old paper by Ben that is so old that he forgot. Okay, that's it. I want just to conclude my talk like this, and this is again a picture of the same type of before. Thank you. Yes.
In the first part of the talk, when you do plain gradient descent, right? You don't do any stochastic type.
No, we don't. No.
And then
I mean, it's not plain because we do backtracking. So we reduce the step size. It's an adaptive step size. We reduce the step size so to guarantee that the function is diminishing at every step.
right. So I also was thinking another thing. What you do is that you use the Runge-Kutta scheme really to go from one stage to the next stage. But couldn't you think about the different layers as the different stage of the methods, like doing a combination?
Sure. Yes. Yes, it's a possibility. One thing that I've not emphasized, because it's so much information always in a talk, is that what we are, because we are comparing methods with different order, in principle, you are computing stages for the controls within each method. And this will mean that you will have more parameters in a Runge-Kutta high order compared to a Runge-Kutta order 1. And then we have decided that we are going to consider constant controls throughout a step. Constant parameters throughout a step, just to have something that is comparable. Yes.
I would like to go back to this negative time step, sorry. So when I was asking what is behind, I mean, so if you go back to neural networks and you have to explain to people this thing, does it just change the sign of a parameter? Does it change some architecture? I mean, if you go back to a picture where you put nodes, what is associated to a negative time step? Is it something easy to interpret? Or?
I mean, does it matter even that they're, why would it matter? Because you just have maps.
Is it just the parameter h in front of the f which becomes negative when it was supposed to be positive originally? Is it simply like that?
Well, so one way is, for example, Haber and Rutotto have experimented a lot with replacing the ODE that transforms the data with the Hamiltonian system. So you could have something reversible there, right? And then going forward and going backwards
But here it would be equivalent to having a ReLU like the other way around, so that it's like you just take the maximum of 0 and minus the data.
We use the tangent hyperbolic, I think.
we use the hyperbolic tangent.
Ah,
really.
okay.
But I have not thought of what the ReLU would mean. But typically, well, yeah, I don't want to speculate.
I mean, the statement that you made, that, you know, the usual statement that more layers helps you, I feel like it's not very well founded on, you know, why that's helping. And I mean, one possibility is that it's actually some sort of, it's providing some sort of thermodynamic bath, actually. It's allowing you to get better solutions to your machine learning problem. It's not 100% clear exactly how it's helping with approximation, because if you go one layer, but you do things carefully, you might actually be able to get the same accuracies in many cases. So it's a little bit unclear exactly what the benefit of the deep structure is.
I think that we were discussing this earlier this week, and I think that probably the right thing to do is to, if you send the number of parameters to infinity, is to send both the number of components or the number of channels in the neural network and the number of layers, not just one of them. It could be, at least, but still this is not quite clear.
I think we are overstaying our booking of the room.
I guess so. Thank you very much.
Thank you.